The story told by the soft, slimy sediment of the lake bed and the clarity of the water above it are two powerful insights into understanding the health of our freshwater ecosystems. Sediment shows us the lake's long-term memory, how much organic material is building up over decades. Water clarity, on the other hand, is its real-time mood, how much life-giving light can actually penetrate its surface. Together, they tell us if a lake is thriving, just holding on, or heading for collapse. The buildup of sediment happens when everything from microscopic algae and aquatic weeds to fallen leaves and organic debris from the shoreline sinks to the bottom. As this material settles and decomposes, it forms a new layer. At the same time, the clarity of the water decreases when those same algae are blooming, or when particles of silt and clay are suspended in the water column, blocking sunlight. These two measurements are deeply connected, reflecting the fundamental ecological processes happening just out of sight. To read the lake's history written in its sediment, scientists first need a map. Not a map of the shoreline, but of the bottom. This is the science of bathymetry. Imagine a boat moving back and forth across the lake in a precise grid pattern. Mounted on that boat is sonar equipment, which sends pulses of sound straight down into the water. Each ping travels to the lake bed, hits the bottom, and reflects back up. The time it takes for that echo to return allows scientists to calculate the exact depth at that one point. By repeating this thousands of times across the entire lake, a detailed 3D map of the lake floor begins to emerge. These bathymetric maps are incredibly revealing. They don't just show the depth and overall shape of the lake's basin. The sonar is sophisticated enough to distinguish between the hard, original lake bottom and the thick, soft layer of accumulated organic sediment on top. The map can pinpoint exactly where this muck is building up the fastest. Having this baseline map is essential because it allows scientists to return 1, 2, 5, 10, or 20 years later, create a new map, and lay them over one another. This comparison shows with undeniable precision how the lake is changing over the long term. Sediment accumulates like pages in a book, 1 year at a time. This top layer of soft sediment is a direct indicator of how much organic material has built up. If the ecosystem is balanced, decomposition keeps pace with accumulation. But when things get out of balance, that soft layer gets thicker and thicker. To get a physical sample, scientists can use sediment probes or cores, pulling up a cross-section that shows these layers. A sudden, sharp increase in the thickness of this soft layer is an alarm bell. It signals that something has changed. It could mean more algae are sinking after a bloom, more weeds are dying off, or that the use of chemicals like algicides has killed off large amounts of plant life at once. A thicker organic layer also fuels more nutrient recycling from the bottom, which in turn can feed even worse algae blooms in the future, creating a vicious cycle. This story in the sediment is directly impacted by what happens on the land surrounding the lake. Agricultural practices, for example, can lead to soil erosion, where soil washes into the water, increasing turbidity and harming aquatic life. Likewise, urban development, with its construction sites and hard, impervious surfaces, accelerates runoff, carrying more sediment and pollutants into the lake. By comparing those bathymetric maps over time, scientists can see if the sediment is increasing, if it's stabilizing, or, in the best cases, if restoration efforts are actually working to reduce it. This reveals the true long-term trajectory of the lake's health. Now, let's look at the second vital sign, water clarity. While sonar mapping is a high-tech operation done every few years, measuring clarity can be done much more frequently with a brilliantly simple century-old tool, the Secchi disc. It's a plain disc, usually about 8 inches across and painted in alternating black and white quadrants attached to a measured rope. Scientists, or often a trained citizen volunteer, lowers the disc into the water until it disappears from view. The depth at which it vanishes is the Secchi depth. It's that simple. A greater Secchi depth means clearer water. Taken just once, a Secchi reading is a snapshot, but taken week after week, year after year,
These measurements create a trend line, showing whether the lake's clarity is improving, declining, or staying the same. Clarity is a more dynamic measurement than sediment. It can change quickly. A shallow Secchi depth is often caused by high levels of algae or suspended sediment from soil erosion. A major rainstorm can wash in runoff, clouding the water. Even heavy boat traffic or strong winds can churn up the bottom in shallow areas, temporarily reducing clarity. But over time, the trend tells the real story.
And this is where the two narratives, sediment and clarity, merge into one. They are locked in a feedback loop. When algae and aquatic plants die, they sink, decompose, and become that soft sediment at the bottom. Therefore, lower water clarity often means there's more algae blooming in the water. More algae leads to more sinking organic biomass when it dies, which in turn creates more sediment. This cycle is a hallmark of eutrophication, the process by which a lake becomes overly enriched with nutrients, leading to excessive plant growth and oxygen depletion. Conversely, high water clarity is a sign of health. It suggests lower algae density, a sign that the nutrient levels are in check. It also indicates a stronger, more balanced food web, where tiny animals called zooplankton are actively grazing on the algae, keeping it from blooming out of control. This healthier state leads to a much slower rate of sediment accumulation on the bottom. Because it changes so slowly, the thickness of that bottom sediment is one of the most powerful long-term indicators of lake health we have. While water clarity can fluctuate season to season, a rapid increase in soft sediment over a decade points to a fundamental and often accelerating decline. And it's the type of sediment that matters. Scientists distinguish between inorganic sediment, sand and silt washed in from the watershed, and organic sediment from dead algae and plants. It's this organic sediment that is particularly damaging as its decomposition consumes oxygen and releases phosphorus back into the water, fueling the next round of algae blooms. This is also where we see the looming impact of global shifts. Climate change, for instance, leads to more frequent and intense rainfall events, which accelerate erosion and wash more sediment into our lakes, EPA.gov. Warmer water temperatures also create more favorable conditions for harmful algal blooms, which reduces clarity and eventually adds more organic matter to the sediment layer, NALMS.org. So, when you put it all together, you get a clear diagnosis. Bathymetry maps the long-term accumulation of the lake's history in the sediment. The Secchi disk measures the immediate health and clarity of the water. Sediment thickness reveals slow-moving ecological change, while clarity shows us the short-term picture of algae and suspended particles. Tracking them in unison tells us everything. If we see clearer water and a stable sediment layer, we know the lake is in recovery. But if we see murky water and a rapidly rising sediment layer, we know the lake is in decline. This data isn't just for observation. It's the critical information needed to guide action. To know if strategies like dredging sediment or establishing shoreline buffer zones are actually making a difference. These simple measurements transform the lake from an opaque mystery into a story we can read, understand, and hopefully rewrite for the better.
The series Bridgewater Clarity is often a reflection of the invisible life drifting in the water column. Now that we can measure the room, it's time to count the guests. Join us for Lesson 8, Who's Growing in the Lake?, where we use microscopes and sensors to identify the organisms responsible for clear or murky water. To go to the next lesson, use the link below. And don't forget to subscribe, like, and share.